Now in this example, we are dealing with a weak acid, which still is concentrated and producing only just one proton, but it is a weak acid. We've been given the concentration of the acid, and we have also been given the pKa value of the acid of 4.1, and we want to calculate what is the pH of this weak acid solution. So first of all, before we get started, let's just simply write down what we would expect. So the pH of this solution must be smaller than 7, just simply because it is an acid, and that is the definition of an acid. So now what is going on here? So let's say this is our acid, and this acid dissociates, and I write it as an equilibrium here. It dissociates into the protons plus the conjugate base. But unlike a strong acid, the weak acid only dissociates to a small proportion. Only very little dissociation is happening. So only very little dissociation goes on, and most of the acid will probably stay in the form of the HA form. Maybe we should make this a little bit larger. So we can actually say, in a way, we can write an equilibrium for that, and we can abbreviate it as Ka, and this would be the concentration of the protons times the concentration of the conjugated base divided by what our acid concentration is once the reaction has reached the equilibrium. We also know that the proton concentration that is generated here must be the same as the acid concentration. So we can write it like that. And with that, we can just simply substitute here. We can write Ka is just simply H, the proton concentration, and instead of the acid, the conjugated base, I also write here the proton concentration. Now what have we got in terms of the HA? Well, the HA, the acid, the undissociated acid, would be, that we have left, would really be our initial concentration. So that's, I indicated with the initial concentration, and that is this concentration here, minus what has been produced in terms of protons. Now, this looks a little bit complicated. In fact, it would be a quadratic equation, but we can do a little bit of simplification, because we can say, well, the acid doesn't really dissociate. So the term H, the initial concentration of the acid, minus what has been dissociated, that is probably still pretty much our initial concentration here, because not much of the acid has been actually dissociated. So we can now formulate, in a way, our Ka. We can rewrite this. We can write Ka equals H plus squared divided by our starting concentration of the acid. And we can use that for our equation for the pH. pH equals minus log to the base of 10 of the proton concentration. So what we need to do is now we need to find this proton concentration from this Ka equation. So how are we going to do that? Well, we just bring this one to the other side, and we've got the proton concentration squared equals Ka times the acid concentration that we had at the start. And what we can do now is we can take both sides negative log base 10, and then we will see what happens with that. So on the left hand side we have negative log 10 of the proton concentration squared equals negative log of Ka minus negative log of the acid concentration, like that. And they are all, of course, to the base 10. Okay, so what can we do with that? We can simplify this term here a little bit on the left-hand side. So this would be 2 times negative log 10 of the proton concentration equals, now we know what this one here is. We know that negative log Ka is nothing else but pKa. And this one here stays log 10 of the acid concentration. We can't do anything with that. Now we also know what negative log of the proton concentration is. This is nothing else but the pH. So we basically have 2 times pH equals pKa minus log acid concentration. And we can also then write a general equation which is actually pretty good. pH equals 1/2 of pKa minus log of the acid concentration that we have here. And we can put in numbers, so we would have 1/2 of the pKa, we had 4.1. 4.1 minus the log of, we had 1.34 times 10 to the minus 1. We need to make sure that this is the correct unit, so mole decimeter to the minus 3 we need, or mole per liter, or this could also be abbreviated as capital M. Now, if we put this into a calculator, we should get for the pH 2.486. So that would be our pH. Now, if we compare it with the pH that we said at the beginning, it needs to be smaller than 7. We certainly find a pH that is smaller than 7. So it looks as if we are on the right track. Now, this one here, that is our equation for a weak acid. And in general, we would consider a weak acid as anything that has a pKa value, say, larger than probably 0. So if we've got a pKa value given and it's larger than 0, we would usually consider that as a weak acid, and we would use this equation here instead of the equation that we use for a strong acid, where we just simply use the pH equals minus log of the proton concentration. So I hope this makes sense, and thank you very much for watching.